Hello and welcome to this class. For this class, we'll look at the concept of atomic size, also called atomic radius. In our last class, when we look at the introduction to periodicity, in our last section, in that first class, I gave you several properties of periodicity, ranging from the atomic size, or we call it atomic radius, ionic radius. We have ionization energy. We have electron affinity, electropositivity, electronegativity, and etc. Right? So we mentioned those properties. I said we look at them one by one. So let's start the first one called atomic size, or we call it atomic radius. So first things first, what is atomic size, or you call it atomic radius? Definition: atomic radius or atomic size is the distance from the center of the nucleus to the outermost electron shell. Atomic radius, or you call it atomic size, is the distance from the center of the nucleus to the outermost electron shell, in brackets energy level. Full stop. In brackets energy level. Full stop. So we are saying this to better understand atomic radius or atomic size. It is simply distance from what? From the nucleus, right? To what? The last shell, called the last shell, and that last shell is called outermost shell. That's why they said that center of the nucleus to what? To the outermost shell. That's your energy level. So we are saying this, please. Let's say I have my K shell, L shell, and M shell, right? For instance, and I have my nucleus here. This is my nucleus. So distance from this nucleus to this last shell. So distance from this nucleus to this last shell is called, let me call it atomic radius. It's called atomic radius, or you call it atomic size. So that's how you define atomic size, or you call it atomic radius. The distance from the nucleus of an atom to the outermost shell is said to be atomic radius or atomic size. This is how you define atomic size, or you call it atomic radius. Now, please listen. I gave you, listen, please listen. Stop writing, listen. I gave you 7 properties, right? Atomic radius, atomic size, right? We have, I gave you 7. Now, listen. For each of them, as we are touching them one by one, we'll be looking at their trends. We call it periodic trends. So as we did the first one, we'll look at periodic trend. As we do the next one, we'll look at periodic trend. As we do the third one, periodic trend. The fourth one, periodic trend. And by the way, you may ask me, what is that periodic trend? So what is periodic trend? Periodic trend will be used in every properties. I'll mention them in every properties. Now, before we now mention them here, what is periodic trends? So let's look at the concept of uh, periodic trends. So let's define periodic trends. So what is periodic trend, please? Define, please. It is a regular and predictable pattern of change in the property of elements as you move across a group or down a group. A regular and predictable pattern of change in the properties of elements as you move across a period or down a group in a periodic table. All right. So here's the task. Your ability to move. Listen to the English. There's the English there. Your ability to move across a period or down the group. It's that's the whole idea behind periodic trends. So periodic trends contain two things: across the group and down. Sorry, across the period and down the group. Don't make the silly mistake of saying across the group down the period. No, check the English. It is across the period, not group. Across the period and then down the group. So this is like the two concept behind periodic trends. So it's focused more on the regular and predictable pattern of change in the properties of elements as you move across the period or down the group in a periodic table. That's by the way. Um, at this junction, I want to try to explain this periodic trend before we start establishing them for each properties. Let's look at directions. Let's look at direction of periodic trends. Periodic trends. So basically, there are two directions when it comes to periodic trends, right? We have the I know I told you from here. We have two directions. We have across the period, and then we have down the group. So two directions, please. Number one. We have across across the period, across the period, and we have down the group. We have down the group. So these are the two direction that periodic trends entails or contain. So as I was saying earlier, that periodic trends will always happen, will always occur. I will always mention them in each of the properties I gave you, reading from this one to the seventh one. I will mention them. So now here's the task. The goal is this: we will look at atomic size across the group. We look at atomic size down. We look at atomic size across the period. We look at atomic size down the group. What is it saying? Also for the seventh one, or the second, third, fourth, we look at each of them across the period, and then down the group. Please, it's not like saying if you're mentioning the word, if you're mentioning the word across the period and down the group, you must be conscious so that you don't make mistake, right? You must be, what am I saying? You must be conscious of what I'm saying. So across the period and then down the group. That's like that. That's so I just try to explain what we mean by periodic trend. So you know, start asking questions. So let's look at for atomic size now. So let's look at across the period. So for atomic size, let's look at atomic size or atomic radius. So let's look at it across the period, please. Across the period. So um what is across the period under atomic radius? Now for across the period, this is the arrow here. So either going this way or in this direction. It is still across the period. So if I'm moving, if I'm saying lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, I am moving in this direction. That direction is called across the period. But if I'm moving this pattern, hydrogen, lithium, sodium, potassium, I am moving down the group, right? That's down the group. So for across the period, for atomic radius, what's the concept there? Please note, atomic radius decreases. Atomic radius, or you call it atomic size, decreases. So please, they might ask you, across the period, what happens to atomic radius, it's what? It decreases. Very, very important, please. It's what there? It decreases across the group. Now, what's the reason why? Why and what is the reason why across the period? If you are going like this, like this, that's across the period. For atomic radius, what happens to it? It decreases. Why? What's the reason? Put up, please. Reasons, please. Reasons, please. Reasons. Number one, please. Reason number one. Increases in nuclear charge. Increases in nuclear charge. Number two. Electrons are in the same shell. Number four. Number three. Stronger attraction pulls electron closer to the nucleus. Stronger attraction pulls electron closer to the nucleus. Right? So this is like the three reasons why we said when you are going across the period for atomic radius, what happens there? It decreases. Why? Because if you observe properly, if I draw out the shell for lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, observe that the atom are smaller, right? The atom becomes smaller, right? So it's more like saying this. As you are going across the period, the atomic radius decreases, right? Atomic radius what? Decreases, right? So if you observe, if I move in this direction, if I draw the shell for neon, fluorine, oxygen, nitrogen, carbon, boron, beryllium, and lithium. If I draw that shell, as I'm drawing that shell, as I'm moving down the group, as I'm moving across the period, this one is more like larger, then second to the largest, and like that. So it becomes decreasing. So as you're moving either this way or this way, so the key take here is this: as you're moving across the period, atomic radius decreases. That is the first thing first there. So what I just did across the period is under what there periodic trends. So periodic trends has two things: across the period and then down the group. So let's look at down the group. What happens there? So down the group, what happens to atomic radius? Down the group. For down the group is what atomic radius? Down the group, what is atomic radius? All right, let's do down the group, please. Down the group. Down the group. For down the group, this is the arrow here. So I use this or this. So down the group. What is what's the concept there? Down the group, please. Atomic radius increases. So down the group. So down the group, atomic radius increases. How good, please? So across the period, this pattern, atomic radius decreases. Down the group, atomic radius increases. What are the reasons why? Please, reason. The reason number one, addition of new electron shell. Makes sense. Addition of new electron shell. Look up this, guys. As I'm moving down the group like this, if you observe the shell for hydrogen, will be different from shell of what? Lithium and sodium and potassium. So here my hydrogen will having one shell, lithium will having one shell, sodium is having more like two shell, right? This one is having more like three shell. So as I'm moving down the group, the shell becomes increasing. That's why I said that addition of new electron shell. Because of that, so as you see that atomic radius becomes bigger because as we're having hydrogen at this atomic radius, helium, that's more of like two shell. So observe it's become increasing, right? Sorry, yes, lithium. If I have sodium, more of like this, right? So it's observed that from here, this distance here, it has double here, it has now triple here. So as I'm moving down the group, the atomic radius, what happens to it? it's because what there it increases. So please note that. So the key take here is that down the group, atomic radius increases. Across the period, atomic radius what there decrease. That's like the concept behind this place. Second reason, also second reason, but reason two, increases shielding effect by inner electron. Increases shielding effect by inner electron. Question please, what are shielding effects? What are shielding effects? Okay, I'll tell you what shielding effects mean in this class. I should have tell you now, but like an assignment please. In the comment section, leave the meaning of shielding effect for me. What is shielding effect? Or you call it screening effect. There are two names to it. Then you call it shielding effect or screening effect. What is the meaning of these things? Put them down in the comment section of this video. All right. I say number two is that increasing shielding effect by inner electron. Number three, the third reason why we said atomic radius increases down the group is because outermost electron are farther from the nucleus. If you observe that, if I put my electron here, this electron here is closer to this one here. This outermost electron is closer to my nucleus. All right. If I draw my outermost electron here, this is my outermost electron. It is now far from this nucleus. So the more I go down the group, the more the outermost electron gets more far from the nucleus. You can see here to this is more closer to each other, more far. Then this is now times 2 far from this nucleus. So as you go down the group, note that atomic what's it called? The outermost electron, this one here, outermost electron are farther from the nucleus. So that's like the three reasons why we consider that atomic radius increases down the group and increases across the period. Right, this is how this concept works. All right, guys. Let's look at types of atomic radius, please. Types of atomic radius. 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 All right. So there are three types of atomic radius. There are three types of atomic radius. Number one, please. There are three types of. Is it recording? Is it recording? Tell me. Is it recording, right? All right. So we said there are three types of atomic radius, right? So we have three types. Number one is called the covalent covalent radius. Number two, we have the metallic radius. Number three, we have the van der Waals van der Waals radius. So these are the three types of atomic radius that we have. Either I call it atomic radius or atomic size, whichever one. So these are three types of atomic radius that we have, as you can see on the board. Let's explain them one by one and see what they mean. So for atomic, let's start the first one called covalent radius, please. Covalent radius. Covalent radius. All right. Let's define covalent radius, please. This is how the distance between this is the distance, perhaps half the distance between the nuclei of two identical atoms bonded together. I said it can be defined as have the distance between the nuclei of two identical atoms bonded together. Bonded together. So, more like saying I am having what's it called? I'm having bonded together. So I'm having an atom this way and another atom which are bonded together. So the nuclei here and this nuclei here, right? So the distance between this nuclei and this nuclei here is what we refer to as covalent radius. So distance between this and this is what we refer to as what? The covalent. So let me call it CR, covalent radius. So distance between half. So look up this circle half, this circle half. So the half the distance between two nuclei is referred to as what? The covalent radius. That's how we define the concept of covalent radius, right? So when do you apply covalent radius? So when do you use covalent radius? So it is used for a non-metal, and also it is used when atoms are chemically bonded, right? Those are the two ways. These are like the criteria for you to use covalent radius. So it is used for a non-metal. It's also used when atoms are chemically bonded together, right? So that's how you define covalent radius. I don't think we need this again. Let me just take it off. Take it off. This is to explain the trends of the table. All right, that's covalent radius. Number two, please. We have the metallic radius. Metallic radius. All right. For this one here, let us call metallic radius. All right. For this one here, it says this can be defined as half the distance between the nuclei of two adjacent metal atoms in a metal lattice. Half the distance between two nuclei of two adjacent metal atoms in a metal lattice. How about this? So that's how you define atomic radius. Sorry, metallic radius. And the concept there is that if I have an atom this way and also other atom this way, the distance from this nuclei here and this nuclei here is referred to as about different. Here they enter each other. Here they are just putting each other aside. So with this one here, so this is called my metallic radius. So metallic radius. So this one from here to here is called metallic radius. And when do you use this, please? The usage. You use this metallic radius is used number one for metals, right? Metallic radius for metals, right? Number two, when atoms are packed together in a metallic structure, they are packed together. So you can see in a metallic structure. That's when you use metallic radius. Finally, let's look at the last one called Van der Waal. Van der Waal. Sorry, it's not wall. Van der Waal. Sorry, mistake. It's double A. Van der Waal radius. Let's look at Van der Waal radius, please. Number three. Let's look at the Van der Waal radius. Let's do Van der Waal radius, please. Number three. Van der Waal radius, please. Van der Waal radius. All right. Let's explain this, please. Also, this can be defined as half the distance between the nuclei of two non-bonded atoms. Half the distance between the nuclei of two non-bonded atoms. So it means that if I have an atom this way, if I have an atom this way, and other atom this way, we said the concept here is they are not bonded. So if they are not bonded, it means they'll be separated, right? So the distance between this first nuclei here, and second nuclei here, please do not mind my drawing. Do not mind my drawing. They must be of the same size. So you can use your compass to construct them. So distance between this one here and this radius here. So distance from here to here is called um, Van der Waals radius. Van der Waals radius, please. So distance between two um, unbonded atom is distance between them is called Van der Waals radius. All right. When do you use it? So use it, please. Use it, please. When you use it for noble gases or atoms that are not bonded. It is used for noble gases or atoms that are not bonded. That's when you use Van der Waals radius. So I gave you definition, the structure, and when to use them. I gave you definition, structure, and when to use them. I also gave you definition and structure and when to use Van der Waals force. All right, this is like the whole concept behind um, atomic size or atomic radius. See you in the next class. We will look at the concept of atomic volume in our next class. If you find this class helpful, do want to share to your classmates, your friends, and also subscribe to my channel for more tutorial videos of this nature. Right? Also, do well to reach out to me if you need my assistance or you need a one-on-one section with me. You can also book a class with me. Aside that, I have a WhatsApp channel and a WhatsApp group. The link to these two groups are in the video description. So check this video description. You see the link to this WhatsApp group. Right. So see you guys in the next class and welcome to Excellent Link Academy. Right.